Hello, this is Tor Lacey with a lecture about plate tectonics. Plate tectonics. What is it? Let's consider the words that make up the name, plate and tectonics, because like much of the vocabulary in the earth sciences, the name is rather self-explanatory. The first word, plate, refers to an individual piece of the lithosphere. The second word, tectonics, is the global assembling of the structure of the lithosphere. In other words, the architecture of the lithosphere. Earth is unique in our solar system in that it is the only planetary body we know of that has active plate tectonics. So why is this the case? Earth's core is still very hot, about as hot as the surface of the sun. The heat that is perpetually rising from the core is trying to escape into space, but the Earth's rigid outer shell, the lithosphere, acts as a barrier. But this barrier is only so strong, and eventually the rising heat splits the lithosphere apart through a process called rifting, and the heat escapes. This rifting has broken the lithosphere into about 20 individual pieces called lithospheric plates, tectonic plates, or simply plates. Consider a hard-boiled egg that has a cracked shell. An individual piece of shell is a plate, while the line of contact between two plates is a plate boundary. The squishy white of the egg beneath the lithosphere is the asthenosphere. Unlike the pieces of shell around the egg, the lithospheric plates are in constant motion around the Earth. This tectonic process creates the structure of Earth's crust and is driven by heat rising up from Earth's very hot core as convection currents. Plate tectonics is a theory that Earth's rigid outer shell, the lithosphere, is broken up into individual pieces, plates, that move and interact with one another along plate boundaries, driving Earth's constructive geologic processes and controlling the structure of the crust. From a historic standpoint, this relatively young explanation for the workings of the physical Earth is comparable to the theory of evolution in biology or the theory of relativity in physics, because it caused a major shift among Earth scientists in our understanding of how the physical Earth evolves over time. In this way, the theory of plate tectonics represents a paradigm shift. How did the grand unifying theory of plate tectonics come to be? While it might seem hard to believe, it wasn't long ago that the generally accepted idea was that Earth, its continents and oceans, formed only a short time ago, maybe as recently as 6,000 years ago, and since that time, Earth has remained relatively unchanged. The paradigm shift to using plate tectonics as the explanation for the geologic evolution of the Earth over billions of years started about 100 years ago by Alfred Wegener and his continental drift hypothesis. Alfred Wegener was an Earth scientist that lived from 1880 to 1930. He brought a relatively obscure idea into the mainstream, that the continents had once been joined together and since that time have drifted apart. In the spirit of the scientific method, this bold notion was tested by scientists that both embraced and doubted this hypothesis. Here are some of the data used by Wegener and others. It had long been noted that the shapes of continents on opposite sides of the Atlantic Ocean matched up. Wegener was able to show that they did match by comparing the shapes of the edges of the continental shelves. This was significant because the edge of the continental shelf, the portion of the continent that is below sea level, represents the true edge of the continent as opposed to the shorelines, which do not. He also showed that rocks of the same type and age, as well as matching mountain ranges, could be found on continents separated by the Atlantic Ocean. Fossils of the same organisms can be found distributed amongst the southern hemisphere continents, which are now separated by thousands of miles of ocean. This shows that at one time, these landmasses were joined together as a single landmass that was the habitat for these ancient organisms, because it would have been impossible for them to swim from one continent to another thousands of miles away. Today, there are coal deposits that originated in coal swamps, ancient sand dunes, salt deposits, and corals preserved as rock, and rock scarred by glaciers distributed in a pattern that only makes sense if the continents were once joined together at geographic positions significantly different than today. Considering this compelling evidence, as well as more that wasn't discussed, why did Wegener's hypothesis not become the theory of continental drift? He was unable to explain how the continents move. Unfortunately, he, nor did anyone else at that time, had a complete understanding of the structure of the Earth. There wasn't a notion of a lithosphere or a asthenosphere, let alone tectonic plates. Without that data, Wegener devised explanations for the movements of the continents that did not stand up to scientific scrutiny. So when he died at the age of 50, his hypothesis died with him. World War II was a terrible thing, but it did bring about new technologies that have helped improve our understanding of the workings of the Earth. One such technology was sonar, which allowed us to map the seafloor. This video is included in your lecture textbook reading, and I strongly encourage you to watch it if you've not done so already.
1912, a German meteorologist named...
The exact correlation between oceanic earthquake epicenters and the mid-ocean ridges and deep ocean trenches provides powerful evidence that the ocean floor is dynamic. It is not static, but instead it is in motion, and because of this motion, the continents are moving as well. The correlation between earthquakes and seafloor features led to the seafloor spreading hypothesis, and eventually the theory of plate tectonics. To review, the theory of plate tectonics describes how the Earth's rigid outer shell, the lithosphere, is broken up into individual pieces called plates. The plates move and interact with one another along plate boundaries. If we remove the earthquake epicenter data from the map above, we have a world map like this. This map shows the locations of the plate boundaries, which correlate to the location of most earthquake epicenters, as well as the locations of growing mountains and active volcanoes. Where two plates meet and interact is called a plate boundary. There are three types of plate boundaries: divergent, convergent, and transform. Divergent plate boundaries mark the location of two plates moving away or diverging from one another. When both plates are oceanic, the process of seafloor spreading makes new ocean crust, while pushing the two plates away in opposite directions, along with the continents that might be part of the plate. Take South America and Africa, for example. This process also provides evidence that plate tectonics is happening because we find the oldest crust along the Rift Valley of the mid-ocean ridge, and progressively older crust the farther we are from the plate boundary. The only reasonable explanation for this pattern is that magma rises up as the seafloor rifts apart, filling in the gap and solidifying as new basaltic ocean floor. This rock is then split in two as each plate moves away. A great place to see a divergent boundary on land is Iceland, which I had the good fortune of visiting with my son a few years ago. Rifting also happens within continental lithosphere through a process called continental rifting. This process can lead to the crust eventually splitting into two pieces as a new plate boundary is formed. Two plates collide along convergent plate boundaries. When one or both plates are oceanic crust, then the process of subduction occurs. Subduction destroys the old oceanic crust. On the other hand, subduction generates magma, which rises up to Earth's surface to make a line of volcanoes parallel to the trench called volcanic arcs. When two continental plates are colliding, subduction ceases, since the crust on both plates is too buoyant to subduct. Where two plates are sliding past one another horizontally, without crust being created or destroyed, we have a transform boundary. Almost all transform boundaries occur on the seafloor and play an important role in allowing seafloor spreading to occur at different rates along a mid-ocean ridge. In some places, though, transform faults cut across continents, where they can pose a significant earthquake hazard. The San Andreas Fault in California is such an example. Plate tectonics is a driving force for Earth's constructive geologic processes. Along plate boundaries, the processes of seafloor spreading and subduction, and on land, continental rifting, make magma and cause tectonic uplift. Magma solidifies into rock and drives volcanic activity, and tectonic uplift builds up landforms like hills and mountains. This illustration gives us a cross-sectional perspective of plate boundaries and the action of plate tectonics. It also shows a hotspot. Hotspots, like their name implies, are spots on Earth where it is hot. More specifically, hotspots mark the location on the crust where extra heat rising through the mantle as a plume melts rock in the lithosphere to make magma. The magma rises up to make volcanoes. Hotspots, along with divergent and convergent boundaries, are the places on Earth where volcanism occurs. Hotspots also provide evidence of plate tectonics. For example, the Hawaiian Islands are an archipelago or line of volcanoes that grew to above sea level to make islands. The only island with active volcanoes is the island of Hawaii, because it is sitting on a hotspot. The volcanoes of the other islands, Maui, Oahu, Molokai, and Kauai, are all extinct because they have been moved off the hotspot as the Pacific Plate moves north. This is the end of the plate tectonics lecture. Thank you for your attention.